Yeah, so we're gonna just go over these general questions today. So there was a QR code at the beginning. I'll just go back a little bit. I realize it's kind of laggy because of the whole giant screen sharing system. So I will try to not go too fast. Not that QR code. This QR code for anyone who's checking in. And for anyone who's online, again, it just got sent in chat. Okay. I am just gonna jump into the next topic. Okay. So this is another QR code. We love our QR codes here. I'm going to send the link in the chat as well. But this one is just going through the first question in the discussion worksheet. So it's completely anonymous, and it's just to get a gauge of how everyone's feeling about these topics. So just take a couple of minutes to go through and try and answer them as best as you can. None of them are required, so take your best shot. And I guess in the meantime, if anyone has any other questions, feel free to raise your hand. We have two lovely AIs here to help out, Maddie and Sydney, right? Yeah. This is discussion 2. So see, we're lagging one behind the regular week because it's for anyone who's kind of maybe lagging a lecture or wants review, or who just wants extra content. So we're running on a Tuesday through the following Monday schedule. Hi, you're here for discussion, right? Okay, cool. Discussion worksheets are up here. Oh yeah, also feel free to take the giant one if you want a cool looking one. It got printed funny, so yeah. Okay, let's start going over the pre-check questions just for the sake of time, because this section always, or this discussion always winds up going way over time. But for question 1, okay, I realized I gave away the answer, but for the first question, we have C is a pass by value language. I give it away, but that's true. Does anyone have any questions or just conceptual, I guess, misgivings about that particular question? So really quickly, just as review, pass by value is defined to be the kind of when you call a new function, the program copies the value that you pass in and then gives it a new kind of local value. So when you we'll see this actually in a couple of slides when we start. You can't see that, but we'll go over it in a couple of slides when we start going over function calls and how that looks in memory. So pass by value basically just means copy paste. And that's also why we say, oh, when we handle structs or arrays or things like that, we don't want to just pass in the whole array or pass in the whole struct, because it means however large that thing is, you're going to copy paste the whole thing. And then it might cause the stack to overflow, or just basically we run out of stack memory. Does that make sense? Yeah, feel free to congregate a little. And we're going to be focused on this area. Okay, so for the second question, I won't be able to answer before I actually ask it, but just generally, what is a pointer and what does it have in common to arrays, and how is it different? Any thoughts? Just any comparisons that you might have?
Don't you pass an array by pointing it to its first element?
Mm-hmm.
And I guess the pointer is just like also memory address.
Yeah. Yeah. So the way that they work is kind of similar in the sense that you can always index into them and you can kind of perform similar operations. But like you said, exactly, arrays, the difference between the two, I realize it's kind of hard to share two things at once, which is a bit unfortunate. But I'll just share this. So pointers are just values that happen to be interpreted as memory addresses. So it's just another variable that just holds some sequence of bits, and the compiler or a system decides to look at it and say, oh, I'm going to interpret these as a memory address. I don't know if it's correct or if it's some invalid memory address, but I just know that I'm supposed to be looking at this as a memory address. So sometimes they're valid, sometimes they're not. Pointers in arrays both reference positions in memories and can be accessed in offset. So what that means is like from the start of the pointer, from the start of an array, you can offset by a certain number of bytes to be able to access other values within certain bounds. So like you were saying earlier, what was your name again? Sorry.
That's Bernie.
Uh,
Like Bernie Sanders.
oh, Bernie. Oh, I remember. Okay. I realize now no one has name tags on, so it's a bit unfortunate. But like Bernie pointed out that arrays themselves are kind of like you have the first element, because if you take an array and then try to get the memory address of it with the ampersand, it's going to result in the same value. So you have to access arrays with the brackets. You can't just look at it and say, I'm going to dereference it, because if you dereference it, it's not going to really work. Does that make sense? Okay. Next question is, if you try to dereference a variable that's not a pointer, what will happen? And what about when you try to free one? So dereferencing is using the star operator, and it tries to access the memory address. Same with free, you're trying to access a memory address. So if you have a variable that's not a pointer, so aka not a memory address, what will happen? Yeah, so you get a seg fault. Yay. It's one of the many ways that you can get a seg fault in your program. There are approximately 5 million of them. But something that's kind of special about this is if say you have a 32-bit value and say, hey, I'm going to try to like fake create somewhere in memory that might be able to be accessible. Say, I'm going to try to guess somewhere in the heap that might be able to be freed. If you can construct a value that looks like that and is okay, and then you cast it to a void pointer and then pass it into free, it'll actually try and free that. Albeit it might not be what like you're expecting. And it also might be something that's like completely done by luck, but technically it could work. But 99% of the time, probably closer to 100% of the time, you're going to result in a seg fault, because it's really hard to like guess the correct memory addresses. Does that make sense? So again, it's like interpreting the bits, looking at it, and then trying to access things. And if it's invalid, then it's going to seg fault. Okay, last pre-check question. When should you use the heap over the stack, and do either of them grow? Any thoughts? Okay, so this one's a little bit of a tricky one, because you don't really have a say whether or not memory is going to be put on the heap or the stack. All you can do is I'm going to say I'm going to initialize variable, and that's where they're going to land. So heaps are, as a general rule of thumb, good for large chunks of memory. So say if you need to allocate space for a really big array or 2D array or large structs or nodes, things like that, like nodes for linked lists, that's usually when it's good to use the heap. If you use stack memory, what might happen is you'll have to pass like different various references to that, and you might actually run out of stack memory. So that's what Stack Overflow technically is called, referring to in a sense. We've all probably might have heard of it in the popular online kind of resources, but Stack Overflow is just the kind of state when you run out of room on the stack. You might have heard of this actually back in 61A when we talk about recursive programs and how they cause the stack to just balloon beyond control. And that's why you're like, oh, like you'll have a lot of stack frames open. So that's kind of referencing this area as well. You'll also want to use the heap for when you need to return a pointer whose variable was created locally. So what this means, we'll see examples of this later, but say you need to like say, I'm going to say create a matrix locally, and I'm going to set the values locally. If you want to return a reference to that matrix, you need to be able to have it on the heap, because if you create it locally, then it's going to wind up on the stack. And then so when you actually return from the function, you can't access it anymore. So if you're feeling confused at all about any of the stuff that we just talked about, we're going to go through some walkthroughs in a minute. How's everyone feeling? Okay. Okay, cool. Also feel free to stop me at any point. I guess it's a little harder now if I don't see like your hand raised, but yeah, if you feel uncomfortable about like asking questions in person, you can always join the Zoom call and then just don't join the audio, and then text me through the chat because I have that open. And same for everyone on Zoom. If you have questions, feel free to DM me. Okay, moving on to general C stuff. We're going to just quickly go through some general C typing information before we jump into the real juicy stuff. So C is considered weakly typed, which just basically means you can almost cast anything to anything else. There is no real kind of rule against what you can't and can. It's just that the C compiler might give you warnings, but if you suppress those warnings with like certain flags, then it won't actually error out. So everything in this case is just bits. So you might remember in Java, like if you try to cast things that like aren't castable, then it'll actually error out on you because Java is considered strongly typed. C is not, because we are at a much lower level. And so you can cast anything to anything else, but just cast it at your own risk. So like what I said earlier about having a 32-bit value that you're trying to make an address, you can technically do that. Probably not really good for your program if you do that. Some common types that we have chars or characters. Some people say char, I guess, or chars. They're always 8 bits, which is 1 byte. So something to note is on different systems, you'll have, it says, okay, always 8 bits here. That's not strictly always the case. On different systems, they might like set it to be a different size. But what is always true is that the size of the char in bits is always going to be equal to 1 byte. So 1 char is always 1 byte. Depending on the system, it might like try to force it to be a certain other number of bits, but you don't actually have to worry about that too much. Just think of it as like the base value is 1 byte and everything underneath that is just for pure calculation purposes. An int is a signed integer type. It's usually 32 bits or 4 bytes. It also depends on the system that you're running. So an int is considered a type def, which is basically a nickname for C values. So if any of you were in lecture, it got talked a lot about in the chat at some point. But what a type def and a struct are basically just different ways of kind of reading the bits that you're provided. We'll talk about structs towards the end a little bit and how type defs kind of change that. The C spec only guarantees that an int is at least 16 bits and that it has to be signed. So you can't have an unsigned value being interpreted or being cast to an int, or you're not supposed to at least. And you can't basically make any assumption of it being a certain size. So on 64-bit machines, it might be the case that an int is actually going to be 8 bytes. So size of int isn't going to be anything that's specific, that's going to be absolutely set. So on exams, if you say, oh, I need to figure out the size of an int or something, unless it specifically states, oh, int is 4 bytes, you don't want to make that assumption. There are other ways of writing ints. So say like int underscore 32, or sorry, int 32 underscore t. That kind of notation is something that's one level below this because it's a little harder to interpret. But what you can always guarantee is if it says int 32 underscore t, it'll always be 32 bits. Same with say like uint underscore or uint 64 underscore t, that's always going to be 64 bits and it's going to be unsigned. Oh yeah, that's what this bullet point is. So this is going to be used if you have the std int.h header. So this is just another import. And these types are pretty common when you're going to be coding at the C level. So an int star is a pointer to an integer. So this kind of part of before that is actually going to just specify the type of pointer that you have. So you could have char pointer, you could have some struct pointer. The pointers themselves are always going to be a fixed size, no matter what type of pointer you have. So you could have something that's like 100 bytes in size, but the pointer is still going to be 8 bytes or 4 bytes, depending on the machine. So in 61C, we always are using 32-bit architecture, which just means that all memory addresses are going to be 32 bits. The reason for that is because we're going to have 2 to the 32 bytes of memory that we can be allotted to. And because memory is typically byte address, which just means we're kind of reading it through byte by byte, then we need 32 bits to be able to address through all of them. So if that's confusing, you can think of memory as like a 2 to the 32-bit array, 2 to the 32 byte array, and it's just been turned on its side, and you're going to say like, oh, I'm going to start from 0 and go all the way to and index all the way to 2 to the 32 minus 1. We good on that? Okay, so the reason that we don't do 64 bits is because no one wants to write out 64 bits of anything. And also, just as a side note, 64-bit machines are probably what you're all using today. It's what we all have in here. But in reality, we're only really actively using up to 48 bits worth of like memory at a time. So we won't need any more anytime soon. Yeah.
We have access to the slide.
Yes. Oh, shoot, I forgot to post it. So I linked my, I think, discussion folder entirely in the central resources post. So the one pinned at the bottom. So if you go on Piazza right now, you should be able to access it. Did I put this in there? Yes, I did put this in there. So you should be able to access it. Just keep in mind, there's a giant section in the middle that just like looks like the same thing, but it's kind of animated. So if it's confusing, that's why. Okay, pointers themselves are just values. So we can think, yes, as a giant array. More on pointers later. Yes, we're going to be talking about this extensively later on. So the different types of false values that we can have. So the null terminator, this is what all string operations are going to look for at the end of a string or something that you define to be a string. So you could theoretically have some weird struct and then say, I'm going to put a null terminator on the end, and then I'm going to pass it off as a string and pretend that everything is okay. And the string class or string header, I guess, so string.h looks at that series of bits and say, I'm going to try to interpret this all as characters. It might spit out nothing, but it will still work. That being said, if you say want to write a string hello, and you have an array and you write, okay, HELLO on each of the spaces, and then you try to pass that off as a string, it's not actually going to work because you don't have the null terminator at the end, and all string operations look for that character at the end. So what will happen if you try to do something like that without a null terminator is it's just going to segfault because it doesn't know where to end. Does that make sense? Cool. Okay. 0 is an integer value. It also represents false. So if you return something and you want to say, oh, I want to compare against false, you can use 0. And then the null pointer itself. So the null value itself is just a byte's worth of 0. So 8 bits of 0. And sorry. And so null itself can be likened to just being a 0, but it's only 1 byte as opposed to 4, say for an integer. Are there any questions so far? And yes, slides are provided. You can load them and you can also take pictures if you want. So don't worry about not writing down everything. And everything that I'm saying will probably be in the speaker notes later if I find the time to transcribe the ones I haven't yet. So you also don't have to worry about like recording all of that. So there's a question in Zoom chat. So does there always need to be a null terminator? Yes, for strings. And if you are trying to do a string operation. So there was a question, I think, in lecture that was really, really good was if that's the case, like something that was discussed in lecture is if we cycle through an array, we can't actually look for the end of an array. So like in Java, there's an automatic end. We just keep going until it stops. Same for Python, we can just go like array length or like len or something like that. And then we'll be able to stop when that's the case. But for C arrays, you always have to provide the length of the array explicitly. Otherwise, as like array ARR underscore length or something, because there's no actual way of checking for the length of an array. The reason that like someone said, oh, why can't there just be like a null terminator at the end? And we just look for that always. And that's because for strings, we've decided, okay, null terminator is not actually a real character. We don't use that in our English or any other kind of language except for in CS. And so we can say that that is a reasonable value. But say if we have an int array, we can't use 0 for that because we sometimes do use 0. We also can't use the max and minimum values, whatever those might be, because those are valid actual like values inside an array. And same with like say structs. If you have a struct array, you can't just say I'm going to have the end of the array be a null because your struct itself might be null. So that's why like for other arrays it doesn't actually work, which is kind of unfortunate.
In that case, if you were to loop through an array, what would be like the proper way to like terminate the thing?
You would have to actively know, oh, this array is going to be this length and then terminate it when it hits that length.
Okay.
Yeah, so there's no way to look at the array and say that's how long it's going to be. Yeah, just as a note, it seems kind of counterintuitive, but for arrays, you will almost always want them to be dynamically allocated in some way. So on the heap, because arrays are usually pretty long and you don't want to store that locally because you'll probably be using it elsewhere. The one difference I would say is it might be in static memory. We'll talk more about that in a couple of minutes, but that's the alternative. And in those cases, those arrays are also explicitly like declared to be a certain size, so you'll know what size it is. Yeah. Oh. Yeah, a great question. So dynamically allocated is just stuff that is stored in the heap. We'll talk about that. Actually, I think I'll talk about that. Let's see. I think I'll jump to memory basics first and then jump to the dynamic allocation and then go back to the animation part. Does that sound okay with everyone? Okay. So we'll skip these parts. Pointer arithmetic is something that you shouldn't be doing too much. So we'll just cover that if anyone's interested. Okay, so this is general, I think, memory basics, if I remember correctly. Oh, no, just C basics. Okay, so C is something that is compiled versus interpreted. So Java is kind of a combination of both of them, both compiled and interpreted. And then Python is something that is purely interpreted. So the main difference that you can think about between the two to differentiate them is that interpreted code is portable, which means that if you compile it on, say, an x86 system versus like if you port it to one of like the M1 Max that's like new with the new hardware and stuff and CPU, they'll be able to run exactly the same on both sides. You don't have to recompile or do anything. But for compiled code, you'll actually have to just port the source code, and then the machine itself has to do the compilation. So you might have heard of like, oh, compile the source code before you do X, Y, Z. Like those kinds of languages have to be compiled because they are architecture dependent. Okay, so overall, wait, am I talking about call here? Oh no, for some reason I just decided to do the right side first. This confused me for a second. Okay, so basically what happens during compilation is there's going to be a lot of substitutions that kind of go in place. We'll talk more about this in a few weeks' time when we go through the call lecture, but usually what you'll hear is like, oh, I'm going to compile something in order to be able to run it. But that's only the first step out of 4 steps before you can actually run something. But in the labs and in the project right now, you'll end up running an executable and producing an executable. And what that just means is it's something that's going to be able to be loaded into your machine and say, I'm going to start running from this particular location. And then there's some way to tell when it ends. You don't know that, but the machine does know that. So preprocessor macros. Nick talked about this a little bit in lecture. We're going to skip over this for now because it's more call related, but you can just think about these as like the hashtag somethings in the code that you might see. Typing, again, like I mentioned, is technically strict, non-strict. It's just more like conventions make it strict, but you can technically type or cast to anything you want it to. And then GCC with a bunch of flags is stuff that you'll see in lab. Lab 1 is due today, just FYI. But you'll see this in lab 1, lab 2, and project 1, as well as later on in class. GCC stands for GNU C compiler, and that's just one of the many compilers out there for the C language. And then this is what my friend said. I was asking them, I was like, well, how should I describe C? And then they're like, C is like Java, but really hard, and then bites you in the bum sometimes. Memory basics. Okay, memory is contiguous in hardware, which basically means there are no breaks in it. It's separated into 4 overall chunks, and it's separated top down. So what this means is we're going to start with a certain way that the memory looks, and we're going to, instead of like having it on its side like in an array, it's going to actually look like this, and then we're going to read stuff top down. So from the top to the bottom, we start first with the stack. There's technically stuff that goes above the stack, but we don't really care about that in 61C. If you want to know more about it, 152 is your class in 162. Next after that is the heap. It's one giant chunk that's pre-allocated by the system and says, hi, anything that I'm dynamically allocating, which we'll talk about, is going to go in the heap. Static / data memory, you'll hear these 2 words kind of used interchangeably. I personally prefer data just because it's a little bit clearer, especially once we go into the RISC-V section. It makes a little bit more sense. But just something to note, the static part, usually when you hear it, it means like unchangeable. It's like a constant of sorts. That's not 100% the case, true in kind of this kind of memory schema. It basically means these are things that have been determined before, like we've actually run the program to exist. Some of the values might be able to be changed. Say if you have a global array, it's going to be sitting in static data, but the location can't change and it won't just disappear. And then the last one is text/code memory. This is where your executable will sit actually. So once you've produced that, that section of memory is going to actually hold the code that's being run. Are there any questions so far? Yes. Yeah, that's a great question. So compiled is going to usually be more efficient. Something to note is compilers and interpreters, you'll hear them being like, oh, compiled code will be faster, interpreted code will be slower. That's not always going to be the case, because what you'll end up having is like, if you have a bad compiler, it's going to be really slow. If you have a if you have a really good interpreter, that's going to be really fast. But say if you have two kind of generally equal terms, both of them, compiled code is going to be more efficient because they'll be able to look at the architecture and say, I'm going to like make the executable suitable to your architecture, whereas interpreted code has to be able to be run on all systems. Sorry, so it won't actually have as many optimizations. Any other questions? Okay. So permissions, before we get into too many other things, so memory will have permissions. So the first one is called read-only permissions. And as the name kind of suggests, it means that we can't actively go and write anything to that memory. So like say the system is like, I want to look at like memory address 1. It's not actually going to be able to do that because it's most likely going to be read-only. This also means actually that you can't execute it though, because there are certain parts of memory that you don't want to be able to execute because say it might contain something that like will mess up the system, or you just want to like say read data from it, and that's totally viable. It's going to sit in read-only memory or a ROM. And then you'll have stuff like read-write memory. So this is stuff that you as the user can read from, so fetch data from, and you can also write back to. But you'll notice that it's not executable, and the reason is because it's for security reasons. So I won't get too much into this today, but 161 talks like for a good 4 lectures about this stuff. Basically, if you think about it, like, oh, if you have a malicious user and then they say like write something to memory that they know is bad or gonna like shut down your computer or like add a bunch of viruses or something, if it's also executable, then you basically give them free reign over everything. So if you want to guarantee that certain parts, okay, if you write to it, you can't execute it. So it might just be data that like other things read from. Does that make sense?
So does this avoid like reading the data and then changing it and then executing it and then just crashing stuff?
Yeah. So you can think of it basically as say like I guess if you were a bad TA and then you were like, okay, I can read someone's information or like a student's information. I can also change the student information, but I can't send the student's information to the registrar to like give them an A+ when they have like a D or something. So you can only control like certain parts of the process. And then the last one is read, write, and execute memory. So this is, it's really dependent, like which sections this might be, but like, for example, I don't actually recall anything that's like would include both of them, but there is also read, execute memory. This is just something that hypothetically has no lack of permissions and said you can do anything you want. That's bad. The last one's bad. Okay, so this section, you don't have to like memorize any of that. It's just for when we reference it later, that might be useful. Okay, going on to memory structure itself. So this part is going to, we're going to try to go through several different examples of how function. Just as a quick like temperature read, how does everyone feel about function calls and how it interacts with memory? Like good, meh, don't really. Okay, so kind of warmish. Okay, so stop me if I'm going too fast by any at any point. if this will. Okay, so in 61C, you'll notice that the memory goes bottom, kind of low to high. So we start with all zeros. In theory, there's stuff below that, operating system stuff, but we're going to ignore that. And then we go all the way to all Fs, which if we translate to binary, it ends up being all ones. Yeah.
So just a quick question. There, you said the memory is separated into 4 chunks, and top to down is the stack heap dash. That's the same as this?
Yes, actually, that's a great question. We're gonna see that happen in a second. So we're gonna go just look at it from, when I say like bottom up, it's kind of like, okay, goes from all zeros to all ones. Right here, I was just top down was describing like where it kind of sits in memory. So if we kind of look through all of that, we have our code and tech. Oh, I don't know why it disappeared, but we have, hello. Oh, my screen's lagging. Hello. Sorry, I think. There we go. Okay. Sorry, stuff is lagging because it's electronics, but we go from bottom, so code, text memory, and then we go to static data memory, and then we go into the heap section, and then we go into the stack section. So you'll notice that this is pretty evenly spaced out right now. In reality, it's up to the system to decide how much space I want to allocate for each of these sections. Just for ease of like visually nice kind of looking stuff, we're going to have them separated out pretty much, but it's not always the case. Okay, so going from the bottom then, this part that we have highlighted, who can tell me what it might be? Which part of memory is this? Yeah, so this is our code and text memory. And so this is where basically the code that you intend to execute is stored. It's usually considered to be in read execute memory because you have to be able to read from it sometimes for certain values. And then you'll also have to be able to execute it. So in that case, then it has the permission, or the write permission is turned off, and you'll actually see this happening in your code itself. If, for example, if you pretend like you say like, oh, I want to execute at like, or sorry, write to memory address 4, it's probably not going to let you in segfault because it doesn't actually let you write to that section. And this can also include some constants. So we know that includes the code itself, and we also know that constants exist elsewhere, but what kind of constants do you think will live in code memory? So constants are things like, or just things that won't change. Any thoughts? We got something in the chat says maybe globals, maybe. Anything else that might sit in the code or text? So that's actually a really interesting point. This gets talked about a lot more in call, but the libraries that you'd import like or include at the top, basically what that does is it takes the libraries and then it copy pastes them into the code that you've written, and then that gets like compiled. So technically, yes. But the libraries aren't considered constants because constants are just singular values. So like 5 or something like that. So let's write a couple of constants up here. Are there any? Like, okay. How might some constants look in C? Also, I'm going to turn my camera this way. Hopefully someone on Zoom can tell me if they actually see the board or not. Okay. I think this should work. So we have like, for example, maybe like const int say x is equal to 5. Say this is outside of any function. So this is not in a function. That's one type of constant. What's another type of constant that might exist? Like say I have void. Anything else? Okay.
I mean, you can declare constants in the function, but they won't exist after.
Yeah, so you can have constant, like say car local constant, and make it, I don't know, like say f. So yeah, that's another type of constant. What about say if we have like code like, I don't know, just is equal to, say, f plus. Is anything in this a constant? F, yes, that is definitely a constant. Because of this, so this is a constant. Anything else? There are two other things in here. So take your 50-50 shot. Only one of the two is a constant though. The 5, right, okay. So the 5 here is actually a special type of constant. So yeah, process of elimination just doesn't have a constant in front of it, so it's probably not a constant. But yeah, the 5 here is actually going to be a constant, and it's actually going to be stored in the code and text section of memory. So that's really important to know, because if we look at this like it's a 5, like we know that's not going to change. It's always going to be a 5, but it's also not directly assigned to any other variable. So it's not going to sit anywhere else in memory. So the system decides, okay, I look at this. This should probably be in the code itself since it's being executed and it's not like being stored anywhere else. So it takes this and puts it in the code and text. These markers are not great and they're new. I just got them today. Does that make sense why that's in code and text? Yeah, it's just basically saying this is, it can't be changed. Any questions? Okay. Okay, moving on to the next section. What section of memory is the new part? Static, right, static data. Okay, cool. There we go. There is severe lag going on. So these are usually going to contain constants that don't need to be changed. So for example, these kinds of constants would go in there. This kind of constant would also go in there. But something to note here is the variable itself. So the like local s, oh wait, I just realized I was dumb. I used the f here, but it was supposed to be that. Anyways, the local c itself would be in the stack. We'll talk about this a little bit later on. Like the variable itself is declared in the stack, but the value that it's initialized to, because it's a constant, is going to be referencing somewhere in static memory itself. So this is going to be living in static memory. The variable itself is going to be on the stack. Does that difference kind of make sense?
So even though we didn't initialize it as a pointer, it's a pointer. So, in 2 different locations.
Yeah, so what's going to happen is it doesn't like actively point to somewhere else. So like you wouldn't be able to dereference local C and say like this is what it is. But what's going to happen is you'll see this more again. I reference call a lot because it kind of makes things make more sense. Personally, I think it should come before C, but whatever. What actually happens is certain parts of the code gets stored in different sections. So it goes basically under a rearrangement process before it can become an executable. And during that whole process, it's going to look at other code and say, hey, this code that's supposed to be in the static, you contain a value that I need. I'm going to like create a temporary reference to it. And then at the end, I'm going to figure out how to get it back, kind of a thing. So like in your final executable, or like you look at it and it's not actually going to be a pointer because the value it stores is not a memory address. But it does like reference it during that whole process. But no, it's not a pointer. Just to make it final, yeah. And this is usually considered to be read-only memory, most of it. That being said, say if we created something like, see if any of the other pens work a little bit better. Say if we have just is equal to like say some stuff in here. We don't care about what stuff it is. So we know that this int array is going to be outside of the any function. So these kinds of arrays would actually also live in static and static data memory, and that's because it's considered to be a global variable, and global variables all live in static/data. Does that make sense? Okay. So this refers to the state of memory. I won't talk too much about this, but if you're curious about why, you can say after I'll answer that. Just will confuse things a little bit, I think. Okay, then kind of going on to the next part, we have our heap memory. So this is memory that is dynamically allocated, and we're going to take a short segue into what dynamic allocation is before we get too much into this. So memory allocation itself is on the heap. So the difference between this and stack memory, so which is what you might be familiar with, like considered local memory, is that this is stuff that you actively request from the system. So you'll use stuff like malloc or calloc or realloc. These are the three that exist in C. The parts that are like the name kind of like correspond to what they do. So malloc is just general memory allocation. It doesn't care about what's in the memory that it gives you. So it'll be considered to be garbage. Because that's not always what we want. Sometimes we want to use calloc, and that stands for cleared allocation. And this just means that the memory that it gives back to you, it's all been cleared into so that all the bits are zero. So sometimes that's pretty useful. Say if we want to initialize a struct and say, hey, a lot of these fields are going to be either null or zero or false by default. Why don't we just kind of calloc it and then set the ones that aren't? So it makes it a lot easier for us. That being said, malloc and calloc in terms of implementation, malloc is a little faster than calloc just because you don't have to go through all of memory and you don't have to look through it, or the system doesn't rather. So if you really, really care about that tiny bit of like improvement in memory improvement in speed, maybe like you'll want to use malloc instead. For 61C, the only kind of project that cares about the speed of your implementation is project 4. And for that, just kind of as a preface, you don't use malloc, you use the second one. So don't worry about the difference. Yeah.
Yeah, so on the heap, let's say the heap memory is full, and then you call malloc, what happens? And then when you call calloc, what is removed?
What do you mean what's removed?
Like, it's clear allocation.
Oh, gotcha. Okay. So for the first question, great question. That's actually the next bullet point on the other side. But if say you're quote unquote out of memory, I'll explain in a little bit what that actually means. It returns a null pointer. So that's also why if you ever dynamically request memory with any of these three, you always want to check that the pointer that you get back isn't null. Otherwise, you're going to be like acting on a null pointer, and that's going to give you errors. Does that make sense? And then for the second one, so cleared allocation, it just clears the bits. So you should always assume that memory that you haven't explicitly initialized, whether it's local, global, whatever, that it's always garbage, which just basically means I don't know what exists there. It might be something totally valid, but it also might not be. So that's why it's garbage. So calloc decides I'm going to look at that garbage and then I'm going to set all the garbage to 0. So like all the bits that you have in the chunk are now going to be 0 bits.
Right. Oh, wait, what do you mean explicitly?
So like say if we like allocate some chunk of data here, it might be like 0, 1, 1, 0, 0, 1, 1, 1, 0. Like we don't really know what it is. And then the pointer that we're going to be returning is going to point to the start of that. For some things, we might actually want to have it all be zeros because remember if we have paste over here, but we have the null term. Null terminators are considered to be 0, and then the 0 value is considered to be 0, false is as well, and then so is null. And then so typically when you might want to actually use this is say if you have an array or if you have a struct. Say if you have a struct and the default values are any of these, then it's a lot easier just to initialize the struct and say I'm going to call calloc instead, so I don't have to go through and manually set all of those fields to be 0. Does that make sense? Okay. I think you had a question as well.
Yeah.
Oh, okay, good. Okay, so something to note about dynamic allocation is it must be manually freed. So it doesn't mean you go to the memory and say, I'm going to like put you back to where you were. It just means that you want to call the function free. So if you don't call the function, if you don't call free on memory by the time that you return from main, so the main function that that the execution starts from, then it's going to cause memory leaks. So what memory leaks basically are when you lose track of pointers. So sometimes say like, is it okay if I erase this? Anyone want it up? Okay. Let's say after teaching online for a bit, you forget that you have to actually physically wipe things and you can't just create a new page. But say if we have like an int pointer equals, oh yeah. So just as an FYI, in 61C, we usually teach you that you need to like cast it to whatever pointer that you actually have after calling malloc. New line. So you'll notice that we actually use size of int here, even though we said earlier you shouldn't assume the size. The reason is because here we know that we want an int pointer. So we don't actually care like if we know exactly what it is, we just trust that this will be equal to what this needs to be. So after we malloc this, oh yeah, what I was saying is we say that you need to cast it always to the type that you have. You'll notice if you take anything, I think in upper divs that basically uses C, I think 152, 162 again, 161 too. They actually probably won't cast it, and that's just because they work at a lower level, so systems or architecture, and at that point you don't want like things like this, you just want byte level stuff. But for 61C you usually want to cast it. So say if we have this, we've malloc certain stuff, we've done our checks, so we're not actually going to check it. We've pretended we check the pointer. At some point later on we say, okay, we're going to actually do this. Let's say that we have, at some point we've declared a int star pointer that like is fake pointer, and then we decide to do pointer is equal to fake pointer. What's the problem with this? So don't assume anything else has happened, but what's the issue with this?
Taking a pointer that points to like something that and they just keep like rewriting it quote unquote to something else. Doesn't make sense.
Doesn't make sense. Okay. So let's pretend these aren't pointers and say it's like we have an int x and then at some point equals like 5, and then we have int y here is equal to something else, and then we have x equals y. Does that work? Like, does that make sense conceptually?
If they're integers?
Yeah, if they're just regular integers, pretend they're not pointers. So is that code that you might have seen before somewhere? Yeah, so if we do like, if we say had like int x is equal to 5, and then int y is equal to 8, and then we do x is equal to y, that makes sense, right? It checks out, it's fine, it's totally okay, right? That wasn't a trick question, but yeah, the red part is okay. So what this does here is like, well, now we no longer have access to this y, right? Or sorry, to this 5. And now x is equal to 8. Yeah, checks out. Okay. So if we do the same thing, I'm just gonna say like this can be absolutely done with pointers as well, just because. So this the way that it kind of works is the star is sort of like with the pointer itself. So it's a pointer which is represented with a star of type int. So it's not like int star itself is a new data type. It's just saying like, oh, this is a pointer variable of size of type int. So in memory, it would look something like pointer is like referencing this 32-bit section of space, and it's some memory address. So what we're saying is, okay, we have some memory address here stored in pointer. We have some memory address stored in fake pointer. And then this variable, which is just pointer, so it's just, think of it as x basically. We're going to set that value equal to what the fake pointer value is. So if you pretend like the 5 and 8 were memory addresses, we've now set pointer to be equal to quote unquote the 8 memory address. Does that make sense so far? Okay, so why might this be an issue? Based on what we see in the slide too. Okay, yes?
We may not know what this pointer.
Right, okay, so that actually is very good. We don't know what fake pointer might be. So I think Nick also mentioned this in lecture, but we don't, unless we've explicitly say set the values or we've checked that it's null, we don't want to be setting it to things. So that could be an issue. In the chat, Assigning a fake pointer to pointer without freeing pointer might be an issue, and then nothing points to previously allocated memory. So yeah, those 2 points are absolutely correct. Basically, what just happened is we lost track of the 5 when it was normal, and that's totally okay because 5 is just a constant. We can like reset that later on. But over here, we've returned a memory address and we've stored it only in one place. As soon as we reset that variable that it originally was stored in, now this value no longer exists in our frame of reference, because even though the heap memory is still set aside because it was malloc, it was never freed. Now we have no reference to it. And this is what a memory leak is. So this kind of thing is what causes memory leaks, amongst other things. Basically, lack of freeing. In here it was really, really explicit because we could see the fact that like, okay, things didn't got reset. But in your C code, it might be kind of hard to track down where that happens because it can be really, really easy just to forget to free something small. So I would definitely try to keep track of your variables and say like, okay, I must have a 1-to-1. Even if I don't free it in the current like function that I've like initialized or something, I have to then return it and then free it later. So you have one of 2 options. If you malloc something, I'm just going to use malloc for simplicity's sake, but if you malloc something in a function, say A, if you don't free it in function A, then you have to return it and then free it at some other point before main returns.
Wait, so we can never access that memory address again?
Yeah, because we don't really know, unless you like printed it out somewhere and decided I'm going to manually like do that, then you no longer have access to that.
I mean, if we're saying pointer is equal to fake pointer, and we want to reassign what pointer is, then that means we don't want it to be what it initially was. Why do we need to keep track of what it initially was? Yeah, so this is assuming that like we've remembered to do all of the things properly, because sometimes you'll want to reassign a pointer, say if like you don't need that anymore, then if you don't need a block of memory anymore, then you need to call free first, because once you do this causes a memory leak, and memory leaks will eventually cause a fragmentation, which I'll show you in a second, or it'll just cause a seg fault because you might run out of memory. So instead, what you might want to do is like before you do this reassignment, you might want to do like say free pointer before doing this, and then now pointer, the memory address that I was pointing to before, which was what was initialized here, now goes back to where all the other memory kind of lives. And now pointer, it still exists as a variable because it's still on the stack, but the value that it initially held, so the memory address, now is kind of like quote unquote invalid. So now you can reassign it and it'll be totally fine. So if we don't call free, what pointer was initially pointing to the size of int, that space, is that considered garbage?
So can you repeat? If we don't free, it's considered garbage? Yeah,
so pointer points to like the for example, like a 4-byte space. And then you assign it to fake pointer, which is something else. And that 4 bytes of space, is that just garbage?
It might be garbage. It might be something that you had set in the middle, like because I didn't write out everything. Right. Basically what it means is like maybe if I draw it out, it'll be a little easier. So say we have like a 4-byte chunk. Sorry, it's kind of wonky. Say we have pointer that's pointing to this 4-byte chunk of space. So we have 4 bytes right here. Fake pointer is somewhere over here. Sorry, this is so weird looking. So fake pointer is over here. This reassignment process basically says, okay, you no longer have this memory address. So let's say this memory address is like FFBB or something. So pointer holds this value. And now it says, I'm no longer going to hold this value. I'm going to hold whatever this value is. So even if this was totally valid before, it doesn't change during this process. It just means that we are now like a floating block in space and we don't have anything pointing to it.
Right.
Does that make sense? So it's not garbage necessarily.
Right. So when you then call calloc, does that get cleared out?
Call calloc on where? Oh, just like overall. Just
like overall.
Oh yeah, it means that we have 4 bytes worth of zeros here.
Okay.
Sorry.
So then, because my question is like, this is there in memory. So if we keep doing this, at one point we'll run out of memory.
Mhm.
But when you call calloc, all that's useless, that doesn't have anything pointing to it, will get freed up, right?
It won't.
It-
It won't. So calloc, okay. Is it okay if I erase this? Okay. So what happens, I'm actually going to fast forward a couple of bullet points to touch on that. So this will let me. Okay, I will come back to that point in a second. Okay, so these points are still remain. So think of memory as a band or just like a list that the memory continuously samples from. So basically it's kind of like having a word bank, but instead of words, you have a memory bank. And it's going to be as continuous as possible. So how malloc calloc this entire thing works is if there is a contiguous chunk of memory that's at least as large as what's requested, the system will return the pointer and any metadata that's needed for the chunk. Otherwise, it's going to return null. So what this means in practice is there are a lot of different ways that memory can be requested from a system. So we're going to have a list of them. I'm going to try to make this slightly nicer. So we have a memory band here. And so this is before anything has gotten allocated. So I'm going to just say like the system has a pointer called M pointer just to point to the beginning of memory. So the first one we call malloc, or I'm just going to say malloc. Let's say we want to malloc this amount of data. So we're going to call that the red data. And so it's going to, so I'll just use our pointer here for red. So we have access to that. Totally fine. We're all fine and dandy. Okay. Now M pointer no longer should be pointing to the start, right? Does that make sense? Why? Why it can't be still pointing right here?
That's the main data.
Yeah. So now this data has been given to the user to use. So the memory pointer says, okay, this is now no longer accessible to be given to other requests. So it's basically saying this is now no longer considered part of the free list. It's now currently in use. So now this is going to be moved to say somewhere else. The somewhere else is not certain. It's system dependent. So I don't think this was actually touched on in this lecture. It used to be covered. But so I will say this is just like an extra tidbit of knowledge. But there are a lot of different ways that like the next available block or the next block that's going to be returned when say malloc is called can be done. So the most common way is like, or the simplest way is the next available block. So say if the next block that we want to request is, let's use green, is really, really large. Okay, so it's going to be this section. So far we can see that this fits in what's left, right? Or this was able to fit within here. And so the next available block says, okay, M pointer is going to point to right here. And that's where we're going to start looking next time something requests. So the green request came in. It says, I need whatever this amount of data is. Do you have it for me? And it kind of goes through, starts from M pointer and says, goes through and reads, yes, this amount of data is continuous. Memory is continuous. So it will return a pointer to the start of this block and say, this is my G pointer for green. And now this section is no longer valid. So now M pointer is going to say point to the next available portion, which is going to be here. So far, so good. We can get everything that we want. And then we say, okay, well, now I no longer need the red pointer. So we're going to say, we're going to call free on red pointer. And so what this does is it now says, okay, I'm going to give this back to the system and make it available again. So now this is no longer marked as being used, and it gets returned to the free list, which is what is drawn here. So let me. So this overall is the free list. And so now we have, okay, this section of green that's currently in use, this section that's free, and then this section that's free. Let's say now on our next request, we want to request something that's of, let's say, this size. Okay, if we call, or I'll just say this, this size is going to be B because I don't know how large this is. But if we try to do, say, malloc size of B, are we going to get back memory or are we going to get back null? or something else? Any thoughts?
Is the M pointer still or all the way up there?
You can basically think of that as like just being a star. It's just like kind of fake pointer. This is the way that the system keeps track of everything is a lot more complicated. So I don't want to draw out everything. You can just kind of think of it as like any available block is going to be pointed to by something in the system. So it knows where things are.
Should be null.
Should be null. Why?
Because it would look at it'll see that it's encountered some sort of. It doesn't have enough space to allocate to this request.
Yeah, exactly. So we see that like, okay, we have this much space. We still need this little chunk. And we say, okay, well, over here, we have like that much chunk. Why can't we just like squeeze it together? And so that's where the continuous or contiguous part comes in. So it must be continuous in memory. So be consecutive memory addresses for it to be able to return together. The reason for that is because say like one of the options are like, well, why can't we just like fuse these two together and like restart? And the reason is because memory, remember, it's just a big, really, really big array, and all of it has indices. So in theory, like we have 1, 2, 3, et cetera, et cetera. Let's say this is X, dot, 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 and then this is N. So if we have indices X all the way to N, what happens like if we fuse all of this is then we're gonna like say go 0, 1, 2, 3, dot, 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 and then get to X again if we take that over here and bring it all the way over here. But that also means we'll have two X indices at the same time. And that becomes problematic. So if you think about it like, oh, if we have a section in an array that's currently taken up, why can't we just take the free side, like stuff that's not being used and then fuse it together? And that's because then you'll have overlapping indices. And in arrays, it doesn't work. Same in memory, it also doesn't work because the memory addresses are just indices at the end of the day. Does that make sense? It's kind of confusing. There's always a lot of confusion that happens. It's not just hard. It's not wise to do that because we have repeat indices in that case. Like you can't, the system then will have to be like, oh, 0, 1, 2. I'm going to skip a whole chunk, but this is technically X, but not really. Because if I just kept indexing, it would reach X again, but in reality, it's going to be N. So maybe like you could have fake indices, but then how many levels will that go to, right? If we have like malloc free, malloc free, malloc free, that's going to be a lot of layers of like trying to figure out what the right address is.
Right.
So then it gets really, really complicated really quickly.
Wait, so what do you do now if you're full? If you can't do that, do you have to free the green part too?
Yeah. So what actually happens is usually when you try to malloc something, it's because you need it for the next step. It's not just like I'm mallocing for the fun of it. So if it actually like returns null because it no longer has space, usually what you want to do is return from the function because it means I can't progress any further. So I need to figure out what to do with that before I can do anything else. Usually it means that the program just stops entirely. But sometimes like there are alternate ways to get around it.
What happens if you call calloc on that area? I see it's already empty, so calloc wouldn't do anything different from malloc.
Yeah, so all of these like their behavior won't really change depending on like the memory schema. I think the one might be realloc. I'll talk about that in like 30 seconds. But malloc and calloc do exactly the same thing. All it does differently is say like if I said calloc green pointer instead, it would return this and then all of this would be 0 instead of like say whatever is in there right now. So calloc does exactly the same thing. It just retroactively looks at the memory and says, I'm going to clear it all now. So in terms of like where it might error, where it might return null, it does exactly the same thing as malloc.
It actually takes that liberty and goes ahead and deletes that chunk.
Yeah, like I would hesitate to say delete. I would just say sets all the bits to 0 because delete sounds like it like, yeah, I hesitate to use the word delete. It just sets all the bits to 0. Because this is just like a continuous series of bits, right? And then it sets it all to 0.
But then our green pointer would be pointing to some memory address that's all zeros.
It doesn't change the memory address. It just changes the memory chunk. Like
which is like bad, right? Isn't that like dangerous?
No. So I guess okay. Let's say we have our And then we call calloc on it instead. So, and then does its thing. So what happens is like the pointer itself. So we try to get the value. So if we do like, I'm just gonna use pseudo code right here. But if we do print G pointer, it's gonna give us some valid memory address. So it's gonna give us a heap address. And the reason here is because the value itself is different from the stuff that it's pointing to. So the value is the start of where all of this is in memory. So like you can think of it as let's say okay, we have int I equals 3. We have some array, and then we go for I is equal to, I guess we already have that. For I is less than 7, I plus, and then we do array at I is equal to 0. So that's basically what calloc is doing, but array is whatever chunk that you got provided. So it's the pointer itself. So it goes in and sets the data at the address to 0, but it doesn't change like the indice, which is the address. That makes sense? It's like the heap address is the index over here, or the start of the index. And then calloc goes through and looks. So memory is indexed, which is what the address is. So like an array. The array values are different from the indices. Does that make sense? The difference? Okay. Yeah.
Sorry, just one quick thing. You mentioned after we first made the red chunk, you mentioned that there's multiple ways that the memory point has changed, and one way would be to the next chunk. But then in lecture we went over where it was a chunk of given memory and then a little bit of nothing, and then given a little bit of nothing. Now, if the system randomly just selects points to go, isn't that like more cause for you to free memory up, because there's random bits in the middle that may not be enough for like memory that you're giving out.
Yeah, so that's a good point. So what Nick was talking about in lecture is that it was basically like it's just like random selection. So that one, the one I was mentioning was the next best fit, which is basically like I'm gonna look for the next chunk that can house how much memory I want. There's also like I forgot what it's called. I think it's just starting from the beginning. So it's just start best fit. So it looks from the beginning and goes all the way through. Next best fit starts from where we stopped and then looks at the next section. That one he mentioned is random. They all have their ups and downs. Like I think it's been shown in many papers, I think, that I think random is like really middle of the pack. Like it doesn't really gear towards like splitting up memory too much, but it also doesn't like do the best job. And the reason is because like all different programs, they'll actually like try to want different sized memories or memory chunks, and it'll also access memory and free memory in a like more or less random pattern, because you can't really predict what programs want to do. So that's how you might end up with those little bits of chunks, if that makes sense. So that's why random, it's whenever you hear like random values being done, it's usually middle of the pack, because it doesn't favor any one program over another. Does that answer your question? Okay. So, okay, really quickly, just so we can get to the more juicy stuff. Yeah, I think like, let me know if you want to break maybe for a second. But if there's overall enough memory, if the memory addresses are not continuous, it's not considered. So like we saw here, even though we had enough memory, because the memory addresses weren't next to each other, it's not going to return it. Yeah, cool on that? Okay. How do you feel about a break versus just continued? Break, any votes for break? 2 minutes? Yeah, go to the bathroom. Okay, I'm going to pause the recording. And then we'll meet back in 2 minutes. Okay, just to get started again, now that we've taken the giant tangent that was dynamic allocation, we're going to jump a little bit more into what actually goes on when we call a function, because sometimes that can be a little bit confusing on what exactly lives where and what happens when. So heap, okay, read write memory. It's typically not executable because we as users are writing data into the heap, so we don't want to be able to execute that. Like we said earlier and emphasized a lot, it must be manually freed. And it grows bottom up. What basically this means is like you'll have the heap pointer. We'll see heap pointer. We'll see that in a little bit. It'll point to like usually around the bottom of the heap, memory address wise. It'll try to increase linear. It'll try to increase linearly. Like we said earlier, like the different ways of finding heap memory, it depends on the system, what it's programmed to do. So it's not always true that like it's linear in growing bottom up, but that's typically what you'll see in terms of diagrams. So heap pointer starts around there, just in our diagram. The stack, it's memory that's automatically allocated by the system. So this will usually be read write as well. We don't want to risk it, and it will be freed by the system, freed quote unquote. And so we don't actually manually have to take care of it. You'll see a little bit of this in RISC-V as well as in the very, very tiny x86 portion of this class. And then later in 161, if you take it, there are pointers to different portions of the stack as well. And you can technically change it and you can technically set it, but you don't want to usually mess with it directly by saying stack pointer is equal to this, because then you'll mess with what the system is expecting. And it grows top down. So this is almost always going to be the case. So it means that if you allocate more of the stack, it'll start from a high address and then quote unquote increment its way to a lower address. So that's very, very important when it says, oh, we add to the stack usually, or when the stack grows, it grows to a lower memory address. Once you free stack memory, it's gonna quote unquote shrink to a higher memory address. So it's a little bit counterintuitive in that sense. So we have our stack pointer, usually referred to as SP in RISC-V, which is what we're doing in 61C. So far, are we okay here?
Yeah, that's one thing you said. Heap, I mean, yeah, heaps contain larger chunks of memory. Right? So in this thing, I don't quite understand like what's happening. At the bottom is 0.
Yeah.
At the top is like all 1s. But the memory size is the same, right?
Yeah. So here it's just because copy paste is easy than like making all different block sizes. So you can kind of just consider each of these to be the same block sizes. And then we can see like, oh, there's more quote unquote more of static memory than of code memory. But this is just like for illustrative purposes. It's
no, I meant like in terms of the order.
In
like
terms
we
of
said stack first, like top down, right?
Right.
Stack, heap, and then
those
two.
Yeah.
So we said stack and heap, but does that like all ones? I mean, the memory is the same, right? So
what do you mean the memory is the same?
so all zeros or all Fs, the space that's taken is the same because the number of bits is.
Oh yes. You mean for the memory address?
Right, so that doesn't have. So the memory address has nothing to do with the space.
Yeah.
Or the like. I think I'm confusing the bigger number to be like the larger number to be like a
bigger size.
Space.
Okay, so I guess what we can think of is there's 32. So both of the top and the bottom values, they're just basically think of it as indices. So say if we have a 32 integer array, we go from 0 to 31 in terms of indices, right? So we can have like and then in this case, we're just saying that we have 32 bits to express that address. So it's going to be 0, 0, 0, 0, 0, 0, 0. And then for 31, or sorry, to represent 31, we need 5 bits. So it would be 0, 0, 0, 0, 0. And then it grows all the way to 1, 1, 1, 1, 1. Does that make sense? So it's just indices. Okay, so we're going to jump into some functions. Just to check, can everyone kind of like tell the difference between what's bolded and colored versus like the black parts? Not really. Okay. Yeah, so right here, this is bolded and it's attempted to be colored, but it's not super clear, I guess. So right here, we have 2 functions. Main just kind of sets up some locally main variables. And then we have a call to a dummy function, which takes in 2 arguments. Sets a temporary variable to one of them and then returns the sum of both of them. So effectively does pretty much nothing, but it's really useful for seeing where things are in memory. Okay, so first things first, we have our main function. That's where we're going to enter all our function calls in C. And so once we enter that, the first thing that we have is we have our int arg1 equals 1, int arg2 is equal to 2. So those have to be stored somewhere in memory. Where do you guys think 1 and 2 are going to be stored? Which section here? So you can say like the purple, blue one, and then the pink one, and then somewhere else. So where are these two values, 1 and 2, to be stored?
In the function.
In the purple? One vote for in the purple, one vote for in the stack online. Yeah. So they're also constants, so they could in the blue, right? So okay, so when we're specifically talking about the 1 and the 2 themselves, they're going to be in the blue section because they are constants. They're in the code, so they have to sit in the blue section. I also realized I preemptively said something else, but for the person who's Alma online. So arg1 and arg2, absolutely right. They're going to be sitting on the stack because those are local variables. Just the values that they hold are going to be quote unquote stored in code. So if we see this, we're going to push arg1 and arg2 on the stack. The stack pointer itself moves down because now the stack pointer says this is the next position that I want to store information in. So now that we've already taken up one quote unquote chunk, you can just think about the chunks as like arbitrary sizes. We're just using them to look nice. Now that we have two things stored up there, we're going to bump the stack pointer down. So we're going to start at the next available section. So, okay, I went in the reverse direction, but 1 and 2 are going to be stored, like you said, in 1 and 2 here. So for the code, it's usually going to be stored in order just because like it's really, really close in the actual physical code. But you don't have to worry about like where things are stored down here. So far, any questions? Okay, so then next thing that's going to happen, we have our dummy function call. So we notice that our stack pointer or our new stack pointer is going to be bumped down 2 more times. And then we have this lighter pink, lighter-ish pink up there. That's going to be where our old stack pointer is. So we notice that there's a clear difference here. I'll mention why it's different later. But we can also see that in order, we have our arg1 right here, arg2 right here. But on the stack itself, it seems to be in the reverse order. Any thoughts as to why? Goes top down, right? That's so. Oh, sorry. So when we call the dummy function, we have arg1 and arg2, right? Because then C is passed by value, which means that the arguments themselves like are going to be copied. I'm just using arg1, arg2 for sake of convenience here. So, right, so if it grows top down, technically speaking, like if we say, okay, arg1, we want it to grow top down. So arg1 comes first. So wouldn't it be like arg1 and then arg2 down here? And the reason that it's not is because, yes, the stack grows top down, but it gets read bottom up. So what that means is, yes, it's very confusing. But when we say like have a chunk of memory, so in this case, like because those are both arguments, we can think of this kind of deep red color as being one quote unquote chunk of the stack. We want to be able to read that in order from the lower memory address to the higher memory address. And we want to be able to read that in order of what we see in our code. So if we read from quote unquote bottom up here, we've moved this down here. But now if we start from the stack pointer here, which is can you actually see my mouse up there? Oh. Oh my gosh, no. Okay. Okay, I need a laser pointer or like a giant stick or something. Okay, let's, how is this gonna work? Okay, let's just say stack pointer SP normal, the bottom one, that's at a lower memory address than the one on the top, right? So if we start from a lower memory address and then quote unquote add offsets to it, we're going to be able to read arg1 first, and then we're going to be able to read arg2, right? So that's why things are pushed on what looks like to be backwards. So whenever you have, say, like arguments, it's always going to read from like the last one to the first one. And then that's how it's going to read on the stack. Does that make sense? Okay, cool. So now that we have that, we have a bunch of things going on here. So we have our two arguments that got copied onto the stack, and then now now that we're inside dummy, we have a temporary variable that's going to be set to the value of arg2. So these I wish I had my pointer. I wish I had any pointer. So you can kind of, I guess this one's really like faint right there. I think it's clear on the screen, so I'll just say it for people online. But we have our old stack pointer right here, which is where the very last step we finished, like when we were calling the variable was. And now our stack pointer gets bumped, in this case, 4 more bytes because it's an int, 4 bytes down to where the temp sits. And then we can see that the temp points to whatever the value of arg2 is. It doesn't point to that one. It doesn't directly just say, oh, I'm going to look at the stack right there. But it's going to say, okay, I know where I'm going to look, and I'm not a pointer, so I'm not actually going to store this memory address up there. It's just going to look at the value and know where to read from. Does that make sense? So kind of what happens is so you can think of like some of this calculation being done on the system level, but because we know that there are 2 arguments to the function, and we know that each of them are a certain size, in this case int sizes, we know that starting from the old stack pointer right here, 0 offset reads arg1, and then an offset of 4 reads arg2. Yes? Any questions so far?
Yeah, so the arg, are any of those copies that are stored on the stack?
Yeah, so these 2 are copies of up there.
Those 2.
Yeah, and then temp right here reads from the stack itself.
Right.
Why is arg1 and arg2 the same?
Oh, that was space, because I retroactively realized I needed more space and I couldn't be bothered to change all the slides. Yeah. So yeah, that's why those 2 are on the same line. That particular block is just 8 bytes. We're going to just pretend it's supposed to be like that. Okay, so now that we have temp kind of sitting there and we know what the value is and we know what to look at, then we're going to directly just return arg1 plus temp. So what happens here is on the system level CPU calculation kind of thing, it's going to read, okay, the offset of 0 from wherever like the arguments were sitting to read arg1. It's going to add it to the temp value, which is an offset of 4. To read arg2, it's going to set the return value wherever that's stored. We don't care about that right now, to the sum of those 2, and then we're going to return it. It's all on the same line because space. But what happens there is we can see that like no more of the stack gets used right here, right? Because none of this was actually technically, I guess, separate operations. So you'll see more of this in risk 5 about like how all of this kind of works. But if there are no separate operations right here, we don't need an intermediate kind of variable to save it. And so we can just do all of the calculations and then move the stack pointer back to where it was before. So if we go back 1 slide, we can see that SP, so the dark SP, jumps to where SP old was. And then we also noticed that temp arg1 and arg2 in the light kind of pink area, so the stuff that's faded out, we can see that none of the values got cleared. We didn't change anything there. It's just that it's no longer accessible. So there was a lot of confusion about that in lecture itself, asking like, does like the memory get cleared? Is it now garbage? In reality, no, because the stack pointer, like moving it up doesn't change anything. All it is saying is at any operation that concerns the stack, if we try to look in stack memory below where the current stack pointer is, it'll return an error and probably seg fault because we don't have access to that, even if all the values are still there, preserved as it was before. Make sense? Any questions? Give you guys 10 seconds to like process that. Okay. So that's a general kind of function call. So there's a slight alternate, because we noticed that just back there, we didn't use the heap at all. So this is an alternate variable allocation system using dynamic allocation. So you'll notice the main difference between the code itself is, hello, there we go. So here we have we have a call to malloc, and then we have a pointer going on. So it's going to make use of the stack. So as before, we had our dummy arg1, arg2 up. Oh wait, my mouse is there. It's just really, really laggy. Okay. So we have our arg1, our arg2 pushed onto the stack. Oh yeah, what we were talking about earlier right here, when it was all like dark red, was considered a stack frame. So you've heard of this back in 61A. If you don't have any recollection of that, perfectly normal. But a stack frame just contains any local variables, function parameters. So in this case, arguments, and any other meta information that's needed. So here we have the start of our stack frame, which is just the arg1 and arg2 here. And then so we're going to go to our dynamic allocation system. So now we have our temp variable in stack memory. And then we can see the value that it's pointing to are all question marks, because we've currently haven't actually called malloc yet. All we've done right here is declared the temp variable. So now that we actually call malloc, we can see that it actually, we're just gonna like brush over all of like what goes on in the system side, because not relevant to this class, but we can see that the heap itself actually did kind of change. So on a very simplified level, our heap pointer originally was down here, right at the boundary of the pink and white. And then we have some chunk of data that we wanted to malloc, in this case, an int size, so 4 bytes. And then so we can see that our old heap pointer is now kind of faded out. And our heap address, whatever our heap address temporary part was, is now going to be what temp is holding. So temp itself is a variable that lives on the stack. Its value is the heap address temp over there in all caps, which is referring to down here. So it's not what's actually stored in memory, just for the sake of space in this case. But this heap address temp down there is where this block starts in memory. Are there any questions?
Yeah, so it would be safe to say that all pointers are in stack and in the stack, stored in the stack, and then all their memory addresses or the values that they point to are stored in the heap.
Almost always. So if there is a case like we get to erase this. Yes, okay. So yes, it's almost always the case. If it's a local pointer, then yes, it's going to be the pointer itself is on the stack. The memory address is somewhere in heap, so the data that it's pointing to is in heap. But say if we have local pointer, a pointer that's like declared it within a function. So what I mean, the difference between that is, say like we have some function here. We're gonna do, let's do int local. We're gonna do our malloc thing here. I'm not gonna finish it just because space, but this is going to be a local pointer because it's declared within the function. But say if we declared a pointer outside, so like in this case we have a car pointer, and this is not in any function itself. This is going to be considered to be a global pointer. And say if it's initialized in here, the pointer star is going to be equal to pointing to malloc size of car, and then times say 16. This pointer itself is going to be stored within static memory in the pink part itself. So if you did say ampersand pointer, this would be pointing to somewhere in static memory. But in this case, ampersand local would equal somewhere in static memory.
So it depends on, so if you malloc it, malloc it meaning like if you create some space, instead of just declaring a pointer, then it's stored in the stack. But if you just declare the pointer, it's stored in the lowest spot.
Not necessarily. So say if I just didn't do that. So say if I just declared the pointer locally, if you do ampersand local, it's still going to be somewhere in stack memory. If you do ampersand pointer here, it's going to be somewhere in static memory, and that's just because this is where it was declared. So the declaration of a variable is different from its initialization. Declaration is just saying to the system, hi, this sized data thing is going to exist at some point. I don't know when, but I just want you to know that it's going to be somewhere over there. And so it gives it some address. But because it's not initialized, we don't know if, say, like, this pointer is like pointing to garbage. We just don't know. Like, we know where it's sitting in, we know where the variable itself is sitting, but we don't know anything else about it. So that's what the initialization part is for. That's saying, hi, like this. Okay. So I think this is actually shows up on the discussion worksheet. So say we have a pointer P. We're gonna actually go through that question. I think that might help. Let me just take a look at it. So I don't mess it up. I'm gonna actually, I don't know if you two over there can fully see it because I'm gonna work on the board over here. So if you want to come a little closer just for the section, feel free to do that. Okay. So I'm just gonna pull out the sections that are actually relevant. But we're gonna have a pointer P.
Also, does it depend on the type because their types are different? Or like
No, it doesn't depend on the type. Like their type has nothing to do with where they're stored or where they live in memory. So like this can also this can just as easily be an int star. What actually defines where the variables live in memory is where they're declared, not where they're initialized. Huh?
like what does that mean? Like where they declared is in like in my whatever
In your code.
like VS code. That's where it's defined.
Yeah. So it depends on where it's declared in your code. Your code might be in VS Code, it might be in Vim, it might be in whatever you want it to be. But it's basically like in your code structure where it's declared. So in this case, local is the span of whatever function that you're in. So
Right.
So something in main, for example, like here, these are all local variables, but they're local to main.
Right.
These variables are local to dummy. This temp is also a variable that's local to dummy. However, the value that it stores is somewhere in the heap.
Right.
So this gives us, this is just a function that spits back out a value and says, hey, this is some value. It happens to be a memory address. I want you, a regular variable, just to store that stuff. I just know, like, from a visual standpoint as a programmer, that it's going to be a memory address, but on the system level, it doesn't get really treated any differently. All it says when it compiles is like, I see the star. I know that the variable temp is going to be holding a memory address, and I'm going to access that as if it's a memory address. So if it makes it any easier, you can kind of like, what I like to say is like, you can think of memory addresses as just numbers, bits, whatever helps you, that we happen to be able to look at and say, hey, there's a corresponding place in the memory structure for this. So you can treat it in all other aspects the same as, say, an int. So just really quickly to walk through this example, it might help a little bit for pointers. I'm going to use just A, B, C in terms of addresses because I don't want to write out everything. So this particular memory address is just going to be A. This one's going to be B. And then we're going to say this holds some value C. And then this holds, or actually that one's short enough where I can write it. This holds hex value to A, and then this holds X, some value X, which is equal to hex value 61C. Okay, so we know some things up front based on the diagram. So this is going to point to this, and this is going to point to this. And then, yes, I think, okay, that is what we need to do. Okay, so what does this actually mean? So if we try to do evaluate the star of pointers, so dereferencing it, what we do is we follow the pointer and go over here. So that gives us the value 2A. But what happens if we try to do, say, ampersand P? So this equals 2A. What does ampersand P equal? So ampersand gets us the memory address. All of these are memory addresses, A, B, C, and D. So it gives us what?
C.
It gives us, so one of the answers is a C, so let's see. C, what else? Sorry, B or D? B, so we have B. Okay. So can you see why it's very easy to think it's C? So what you actually said there, C is a correct answer for something later on. But for this one, it's actually going to be B. And the reason is because we know that this is the variable and it sits at position B. But the value that we actually have, if we try to do like say print P, it's going to give us C. And the reason for that is because at this position, we actually hold the value C. So the value it holds is actually C. We just happen to nickname it P as a variable. So that's what it means in terms of initialization versus declaration. P gets declared at memory address B. It's initialized to hold value C. Value C in memory holds 2A. Does that make sense? So in other words, C lives right here. And then when we dereference it, we just say, hey, variable P, which lives in address B, holds the value of C. C just happens to be a memory address. Okay, if we treat it as a memory address, we're going to find it in memory and then return the value. So that's what the star does. Does that make sense?
Yep.
Okay, cool beans. Really quick exercise, go off of that then. Okay, what does star double P equal? P? So if we try to get the value, would we print out P or would we print out something else? Yes, we would print out B. So remember, it never like actually, when we do these kind of operations, we never get the variables themselves. We just get the addresses or the values associated with them.
I mean, is this any different because it's a pointer to a point?
So we know that this is not a variable. This is a variable which inherently holds something else. This is a variable that holds B. We just happen to like nickname it basically. So PP doesn't, or PP and P both, like none of them exist actually in memory.
No. Okay,
We're not gonna be 5 about this.
No, my issue is so if you do ampersand PP, you get A.
Yes.
That's the value that it is at.
Yes. It's where it lives in memory.
Yes, but then star P holds the value.
Oh wait, sorry. This actually messed up. Yes, you are absolutely right. I just realized. Yes, star actually would equal C. Yes.
Yes, but which is wait. So C. Okay, that's the. Let's. Okay. So it would be C, but so P is just the placeholder for the actual value C. So,
yes.
Okay.
So variables, okay, like variables, we think of them as like, oh, they actually take up space. They're just another way of referencing data. Because like in this case, like the data is quite small, but think of it like 100-byte array. We don't want to like directly reference that every time. So we're going to use something that makes it easier on us programmers. Okay, and then so last one then, if we just have this by itself and try to print that, what would it be? A. Why A?
Because we're evaluating the value of the pointer.
Right, so the value of the pointer, remember? Yeah, so we have the address, the ampersand of this variable to be A because that's where it lives. The value itself is like, in this case, we can see it points to this location, which means that the value is going to be the address of what gets pointed to. So in this case, it's going to be B. So the whole like pointers, non-pointers thing, it's kind of funky. Just in green, we're going to make this more clear. So we're going to pretend that these pointers all don't exist. This is what it would look like if it were actual like normal variables. So it would be something along the lines of like, this is B, this is A. So we have P is equal to C, whatever C might be. And then double P is going to be equal to B. And then, so now we can see like following it, ampersand A is equal, or sorry, ampersand this variable is going to be equal to A because that's where it lives. It holds the value of B. And then if we try to evaluate B, aka like quote unquote execute it, we can recognize that B is an address. And so then it brings us to the actual value of what sits there. So which is the value of P. So in this case,
So ampersand is basically where the memory address of where it is located, the pointer
Yes.
itself.
yes,
And then star P is the memory address of the value that it points to. But that's okay. So that's my question there.
wait,
So-
star pointer
No, star PP.
is equal to,
No, I mean whichever it is.
okay.
Like whatever we're talking about, star something. When you dereference it, the pointer, it's the value that it points to. Because star P is the actual value, the
Yes.
hexadecimal value there.
Yes.
And then star PP is pointing to, like, is equal to C, but C is not a value. C is a,
C is a value, right?
but it's
That's
a reference to, I mean, it's the, yeah, exactly, the address to,
This?
to A, right?
yeah. So it might help to look at it in like actual hex form. So let's say C is equal to hex like 3FB4 or something like that. If we kind of just deconstruct this and we turn this into like a base 10 number, it's just going to be the same as like say 5 or like 3,280, right?
Mhm.
So in this case, we know that C is an address, but say if we were to go through and not realize, say like, because we know it's a double pointer, so we know this is another address, but in reality, we could just as easily say this is an int pointer and say this is equal to like 3FB4, which is also an address. So in that case, when we dereference pointer, then it's going to be equal to 3FB4. Does that make sense?
Mhm.
So
So either way, even the thing is like a value.
yeah, either way, it's a value. We just happen to know it's another address here. So we're like, oh, C matches here, so we can go look at that.
Right.
But that would have to require another level of dereferencing. So another star here would give us 0 hex 2A.
Okay, yeah.
Make sense?
Yep.
Okay. So really quickly to go back here, we're gonna just kind of quickly, how much time? Okay, we have 2 minutes. We're gonna try to just skim through this a little bit. So we can see that the heap address itself is given, and then we didn't actually like set it to anything, honestly. And then the next point is, did I just entirely skip over that? Okay. So if we go through this and say we don't actually look, we set the value at some point, which is over here, we can, it's going to be set, and then we return by trying to dereference it. We can see that as soon as the dummy function returns, the stack pointer goes back to where it was before, and then the temp, like what it was referencing, now no longer references it, right? Even though the value itself has stayed, we now no longer have access. So we can see that the heap address pointer just effectively in our eyes disappears. So that gives us an issue. The heap address temp down there, the block is still active, so it hasn't been freed. And so this is what a memory leak kind of looks like in memory. So it's basically still active, but we no longer have the reference to it.
Looking at the faded.
Yeah, so it would have been referenced here, but now we don't, because we don't have access to temp, we can't dereference it or use that pointer anymore.
And that creates like fragmentation.
And it creates memory leaks, which is bad. Okay, so in that case, this is actually non-optimal. So it's what happens to the heap address temp, it's not freed and will forever live in the heap until our program dies. So the way to kind of actually kind of fix that is what we can do is we can say, okay, well, we're going to actually return the temporary pointer instead. So like the difference between this and the previous one, code that changes right here. We just call it. We don't actually return anything. Here, we're going to return the int pointer and say, hey, if we don't want to directly free it up here, because in our previous function call, we wanted to use star temp here. So we couldn't feasibly free it before that. So if we want to use it, then we say, okay, well, we're going to set it to whatever. And then we're going to return the star temp pointer instead. And so as soon as we have it freed, then we can free that. So now that we have this going on, we have a temp pointer that has been declared locally. Stack pointers goes down because this is a variable that's local to main. This temp pointer now is holding the value of heap address temp. So if we decided to print temp pointer, that's what we would get back out. Then we call free. We can see that kind of the heap memory faded itself, and the heap pointer doesn't necessarily go back to where it was before, like we talked about earlier. We have no guarantees of where it'll live. And so we just know that now that memory is freed, it goes back in the free list, and we are all good to go. So why doesn't HP return to the original position? Well, the heap isn't necessarily used linearly. Depending on the replacement policy, which is what we were talking about earlier, the heap memory will be sampled and quote unquote merged differently.
I mean, it doesn't matter where it points, right? Because when you dereference a pointer to some space in the heap, the pointer will move to that space.
You mean heap pointer HP?
Yeah, so like I have a pointer in the stack. It's pointing to some place in the heap. There's a memory allocated there. If I dereference that pointer, the heap pointer will go to that space, right?
The heap pointer is just kind of an abstract representation of how like memory chunks get tracked. So that's why like HP isn't something that the user is supposed to like know about really. It's just a visual representation of like what's going on in heap. It's saying like, oh, now this is free. It doesn't necessarily get bumped back to where it was before because we don't know where the system wants to sample memory from next. So that's why. Unlike the stack where it always goes down linearly and then goes back linearly. Does that make sense? Okay, so technically there's one more section for this. I have written the notes for all of this in the speaker notes, so you should be able to access it from your slides. I'm not sure if you can access it on the tablet to see the speaker notes, but I'm gonna go back tonight and add some more stuff with some of the things that we talked about elsewise. Yeah, thanks for coming to discussion. It was a long one. Hopefully it was helpful.
Thank you.